Okay, so Newton's second law is just an equation. And the way that that's usually written in textbooks is one of these two ways. So either the net force, F net, is equal to ma, or the exact same equation just rearranged to have our a alone on its own side is a equals this F net over m. So we've worked with this in class, but our F net, that is the net force, which I'll talk about in a second. But just like forces have been measured all year for us, the units for that are newtons. For this m, that's the mass of some object that we're focusing on. And just as it has been all year, our most common unit for mass is going to be kilograms. And then the a is the acceleration measured in meters per second squared or meters per second. So I'll put both of those kind of equivalent units right here. There's no conversion needed between meters per second and meters per second squared. They're the exact same thing. Now, what Newton's second law really tells us is it can relate the net force or the sum of forces acting on an object to its acceleration. So it will tell us if we exert these 5 forces on an object, how it's going to react or how that is going to change its motion, or maybe it won't change its motion. So one of the very sort of basic outcomes of this is if we look at an example of pushing this 50 kilogram object and we exert a 100 Newton force to it, it's accelerating at 2 meters per second squared. Now let's think about what might happen if we exert the same exact 100 Newton force on something that's twice as massive. So now this 100 kilogram bucket of water, let's exert the same force on it, 100 newtons. And now its acceleration is only 1 meter per second squared. And acceleration, remember, is a change in motion. So in this case, we're speeding up this tub of water or this bucket of water, and every second its speed is increasing by 1 meter per second, or 1 meter per second every second. That's why these units look kind of weird. But then if we go back to this 50 kilogram thing, it's half as massive. Now it's speeding up, and it's getting to the same speed twice as fast, so now it's accelerating at 2 meters per second squared. That's the fundamental relationship that Newton's second law is showing, is this relationship between mass, between the net force or the forces we exert on this object, and this object's acceleration. One way that you could think about it, if it helps you, if this helps organize your thoughts, the net force is kind of like a cause of a change in motion, right? When we exert forces on an object, and if those forces are unbalanced, it will cause an acceleration, which is kind of like the effect, right? A net force is the cause, the acceleration is the measured change in an object's motion. It measures the speeding up, or if we exert forces in the opposite direction, the acceleration now will measure how quickly we are slowing down and the rate of that object's velocity change in the opposite direction of how it's moving. Now, the way that we've used it in class is not only for those kind of like qualitative comparisons of knowing that more massive objects take more force or would take longer to reach the same speed as a smaller object, or at least an object that is less massive. We've used this in free body diagrams. And we'll do that right now for this crate as we push it. Now, I want to turn friction on here so that we have a slightly more complicated example. And let's look at the case of us, or this mannequin, I don't need to take credit for it, pushing this crate, or this box, whatever it is, to the right with a force of 150 newtons. That will be an applied force, and the simulation labels it as such. With 150 newtons of force. And then pulling to the left is this force of friction, and that is 77 newtons to the left. Now the simulation doesn't show the other forces acting on this object, but we know, hopefully feel comfortable with, the fact that as long as we are on some planet or near some very large mass, there will be a force of gravity acting on this object. And in this case, we don't need to worry about how to find that force of gravity yet, but it would be 490 newtons. We'll talk after this quiz about how I know that force of gravity is 490 newtons. But knowing that force of gravity, we can also figure out what this normal force is. So a normal force, again, since this object is sliding along the ground is a stable surface and will exert this sort of force to keep our object from going right through that stable surface. So like the ground, tables, desks, walls exert normal forces to keep us from being able to go right through walls. So that is a normal force. And it must be equal and opposite, or equal to our force of gravity. That's why this box, as we're pushing it, as the mannequin is pushing it, is not sinking down into the ground and it's not flying up into the air. Now, where Newton's second law comes in, and we'll look at how the simulation calculated this acceleration, is we first need to figure out the net force. And again, the net force we can think of as like the sum of forces, or almost like a total overall force acting on an object. But you might notice sum usually means that we add. So we only add forces up, like literally, sometimes. In this case, in order to find this net force, or the total overall force, we would have to do 150 minus 77. So if we were finding our net force, it would be 150 newtons minus 77 newtons to get this net force of 73 newtons. And even though the simulation doesn't write the word out, it shows that net force is to the right. And the way that we know that the net force is to the right is because the total force pushing this object to the right, 150 newtons, is greater than the friction force acting left. So the net force points in whatever direction we have more total force towards. Now, one thing that I want to point out here with this net force discussion, we could have a net force in these vertical forces as well, or in the vertical direction. In this case, and in all of the examples that we've looked at in class so far, we've only either had a net force horizontally, left and right, or vertically. We could look at more complicated examples where we have an imbalanced net force, both horizontally and vertically. It would just take some trigonometry, some Pythagorean theorem, some vector addition that, frankly, isn't any harder conceptually. It's just more math for us. So we'll just look at this like slightly more simple example for now and at this point in class. So we have our net force, 73 newtons to the right. But that still doesn't answer the question of how the simulation knew what the acceleration should be, or how they estimate the acceleration of this 50 kilogram object. So in order to do that, we're going to use this sort of second form up here of Newton's second law. So acceleration is equal to our net force, 73 newtons, divided by this mass of 50 kilograms. And if you plug that into a calculator, whether that's Google's calculator, a phone calculator, anything, an abacus, then we should get the same thing that they got, 1.46 meters per second. Or you could write 1.46 meters per second squared. Now I do also want to include the direction here, because the simulation, one bad thing about it, it doesn't tell us the direction of the acceleration. It does show the sign, positive or negative, but positive and negative signs is kind of arbitrary based on the coordinate system that they've set up. So I prefer to work with the directions here. Now, one really important thing that we've talked about in class is that acceleration is always, always, always in the same direction as the net force. So since we have more force acting to the right than to the left, our net force was to the right. And since our net force was right, so is our acceleration. Now, what this means could depend on how the object was already moving. So I'll get an example of this now. So since this object is moving to the right, and I'll just let the simulation play for a second. It's moving to the right, we can see that. This object is being pushed to the right by the mannequin, and it's moving to the right. That tells us that the velocity is to the right. Velocity is just an object's motion. So if we know the object is moving right, its velocity is right. And we know that its acceleration is to the right. because the net force is to the right, because we have more total force acting to push this box to the right than friction pulls back to the left. Since our velocity is to the right and this object accelerates to the right, this answer for acceleration means that every second our velocity, or the box's velocity, increases by 1.46 meters per second. So we'll be able to see that here, right? That's how fast the speed is going up. Every second we push this, or every second the mannequin pushes it, the speed, or the velocity of that object, to be more specific, is increasing by 1.46 meters per second every second. That's why we have this kind of weird unit, meters per second per second. That tells us that this is speeding up. Now, if we had just a slightly different situation, so I'll leave all of this here, and let's say that we now have a 150 Newton force acting to the left instead of to the right. Notice real quickly that when we do that, and I'll click play for a second here, the object is still moving to the right. So I'm just going to make a note to myself that our object's velocity is to the right still, even though we can see that both forces acting in the horizontal direction are left. We still have our force of gravity, that's 490 newtons. We have a normal force, which is also 490 newtons. And now we have a 150 Newton applied force, and a 77 Newton still friction force. And there are no forces still pushing this object to the right. Now that seems kind of counterintuitive. This object, its velocity is to the right, and we can see it moving to the right, and yet there are no forces continuing to push it to the right. That's an example of Newton's first law. This object was put in motion to the right. It tends to stay in motion to the right unless we have these unbalanced forces, which we do, acting on it in order to slow it down. So in this case, if we wanted to figure out how did this simulation get this different acceleration, we can use Newton's second law again. So now, you might notice, to get this net force, or the total overall force acting on this object, we still don't really have to worry too much about Newton's or about these vertical forces, because 490 minus 490, those forces go in opposite directions, so we subtracted. Those cancel out. The net force vertically is just 0. So we really only have to worry about the horizontal forces in this case. Now, since these two forces are going the same direction, they work together. They're additive, and so we're going to do 150 newtons plus 77 newtons. And that's how they got that number 227 newtons for their net force. And they didn't write it, they used their vector in the simulation for this, but I'm going to write it out that force, that net force, overall total force, is 227 newtons to the left, acting on this object. Now, that's the cause. That's what's happening to this object, or that's what's being exerted upon this object. Overall, the net effect is basically 227 newtons to the left. If we want to figure out how it's accelerating, we use Newton's second law now. Acceleration is equal to our net force divided by the mass, still 50 kilograms. And if we plug that in, we would get 4.54 meters per second. Again, for the direction of acceleration, it's in the same direction as net force, so since our net force is left, our acceleration must also be left. Now the final piece of this, we have a velocity one way, and that's to the right, because earlier this mannequin was pushing the object pretty hard to the right, put it in motion that way. So that's why the velocity is right, is because the object is still moving to the right. But the acceleration and net force are left, because now, in this moment, the forces acting to the left are stronger than the forces still pushing this to the right. And that's why we can see this speed decreasing. That's why this object is slowing down is because now our velocity and acceleration are in opposite directions. So the overall way to figure out is this object or is this person speeding up or slowing down is we need to figure out what direction is its velocity in, what direction is its acceleration in. If they're in the same direction, this object is speeding up. If they're in opposite directions, if our velocity and acceleration are in opposite directions, that object would be slowing down, which is what we see here. And in fact, if I just hit play a little bit longer, we would see that object come to rest, and now the net force is left, the sum of force, the overall total force is left, and its velocity is left, because we can see it moving to the left. Velocity is just the direction of that, is just how it's moving. It's left. Since our net force is left, our acceleration must be left, and since acceleration and velocity are both left, now we can see this object is speeding up. There's a lot in Newton's second law, but the key things to keep in mind are net force being sort of like a total overall force, acceleration being like the change in motion that's caused or produced by this overall net force, total imbalance in forces, and then figuring out if an object is slowing down or speeding up based on the acceleration's relationship to velocity, or how that acceleration relates to how the object was already moving before these forces were exerted. Now the last thing that we'll do, something that we did in class, which is kind of a strange activity that no one would really ever ask you to do, but is an important conceptual step to be able to do. Net force you can think of as like an overall summary of what's happening to an object. So since we said that the net force was 227 newtons to the left on this object, what that's basically telling us is that if we had a 50 kilogram object or another 50 kilogram object, it would behave the exact same way as if there were just a 227 Newton force to the left. And that's our net force, right? And this object over here would behave the exact same way as this object here, because it still has the same mass, it still has the same net force acting on it in the same direction and everything. So it would behave the exact same way, it would have the same acceleration. That's contingent on having the same velocity too. But if we wanted to do that for this earlier example too, we could with that. So we had an object, again, the mass was just 50 kilograms. 50 kg. And if we wanted to draw another 50 kg object, we could draw all of the same forces, but if we just wanted to summarize it like sort of most efficiently, or we wanted to draw a situation that would behave the exact same way, we could just draw our net force on there. So it's 73 newtons to the right. That's our net force, and this object down here with this net force, or with this one force acting on it, would behave the exact same way as the object with all four of those forces acting on it, because it has the same mass and the same net force, just 73 newtons to the right. Now there are more complicated examples that we've seen in class too, so I'll do those hopefully really quickly before we call it a full video. So if we had some example like this, let's say we have a 30 kilogram mass, we have, let's say, 3 forces acting on this object, and let's say we have 2 forces acting downwards. I'm leaving context out of this problem because the only point of this is thinking about how do we deal with more complicated examples where we have multiple forces acting in each direction. So let's say that we have a 100 Newton force, a 50 Newton force, and a 60 Newton force. And then downwards, let's say that these forces are 70 newtons and 80 newtons. Okay. So actually, I'm going to change that 80 Newton force just because I think it'll be confusing. I was noticing something that was going to happen. Let's change that to 100. Change it to 75 newtons. That'll avoid the confusion I was worried about running into. So if we want to figure out our net force, we can think about this as sort of 2 different groups of forces. We have our forces going upwards and our forces going downwards. the total force going upwards looks like it's 210 newtons. And the total force going downwards looks to be 145 newtons. So we can treat this as if this is a situation that we've dealt with before of a 210 Newton force going up and a 145 Newton force going downwards. And we've dealt with situations like this before. If we just had one force going up and one force going down, we know we would subtract them because they're working against each other. And I skipped over this, but we added these three forces together and we added these two forces together because they were going the same way. They were working together. But if we had these forces going opposite directions, then we could figure out our net force just by doing our 210 minus 145 newtons to get, that looks like it's going to be 65 newtons. And in this case, the net force would be upwards, not because we had more forces acting upwards, but because the total strength of those upwards forces was greater than the total strength of those downwards forces. So our net force, again, it would be 65 newtons up. If we wanted to solve for the acceleration, we would do that just with a division, divide our net force by this mass. It looks like that would be a little over 2 meters per second squared. And that would be upwards as well because our net force is already up. If we were asked, is that object speeding up or down? Let's say its velocity were downwards, but we know that its acceleration is up because our net force is up. Then this object would be slowing down because velocity would be one way and acceleration would be the other way. If the velocity instead were upwards because this object was like thrown into the air or because the object is moving upwards, then this object would be speeding up because the velocity is up and so is the acceleration. So that in that case, it would be speeding up if we had that. Okay, that was Newton's second law. There's a lot in there, but with more practice, this is going to get a lot easier. And in class, we've looked at a lot of examples of objects with different masses, with different forces acting on it, and how those objects will react. That's sort of like the acceleration. One key thing to keep in mind, remember that net force is not a different kind of force. It's think about it as like the total or the overall force acting on an object. Or in the case of these sort of simplifications, you can think of them as like a summary of all of those different forces that are acting on an object. Again, the net force is like the cause for some change in motion, and the acceleration is the effect. That is the object's change in motion.